10.6, we're going to break up into two small parts. And so today we're going to talk about conic sections in polar coordinates. So for all of these, we're going to be placing the focus at the origin. And all three conic sections are going to be defined in terms of what a focus and a directrix. So I'll talk about how we'll make that happen. So we let F be a fixed point called the focus and L be a fixed line called the directrix in a plane. And E is a fixed positive number that we call the eccentricity. And the set of all points P in the plane such that PF over PL equals E will allow us to determine what type of conic section we're going to look at. So it's an ellipse if E is less than 1, it's a parabola if E equals 1, and it's a hyperbola if E is greater than 1. All right. So 4 cases, and this really can represent any type of conic section. These aren't necessarily supposed to be parabolas, they're just supposed to be pieces of conic sections. So if the directrix is chosen to be to the left of the focus as x equals negative d, or if the directrix is chosen to be parallel to the polar axis, so y equals plus or minus d, then the polar equation of the conic is given by the following theorem, which is this. It will be ED over 1 plus or minus E cosine theta, or ED over 1 plus or minus E sine theta. And then depending on the value of E, again, it will give us a different conic section. All right, so real quick, I'll walk you through sort of how I know that this is a conic section. I don't know if I want to go through the full proof. But let's go through at least some basics. All right, so I'm going to put a focus at the origin. There's my conic section. I have a directrix on this side. And it has equation x equals d. All right, so let's put a point P here. And that would make this theta. And that has distance r. All right, and this is line, sorry, this is line L. And the focus, I'm just going to call point F. So by the definition of eccentricity, we have PF over PL, those distances equals E. And one thing, by just the definition of polar coordinates, the distance PF is R, right? That's just that. That equals R. And the distance PL, we can do a little trig to come up with an expression to represent that. So all right, so P to L is this horizontal distance. So it's going to be D minus, and what I want to do is take out basically this distance here, right? Well, let's call that X. Can we agree that cosine theta equals X over R? Everybody okay with that? Sorry for writing so small. It looks big on my iPad. I'm zoomed way in. Cosine theta equals X over R. So X equals R cosine theta, right? Meaning this little distance here is just R cosine theta. So if I want to be left with this distance, it's just D minus R cosine theta. All right, so that means I can then solve for PF. PF equals E times PL. And then I can then put this in terms of polar coordinates, right? So R equals E times D minus R cosine theta. And then I just want to isolate R, so I'm going to distribute E. So E D minus R E cosine theta. I'm going to group the R terms, so R plus R E cosine theta equals E D. And then factor out an R. R times 1 plus E cosine theta equals ED. And R equals ED over 1 plus E cosine theta. And all of a sudden we are at the point at which we have our formula for a conic section in polar form. Now this is a horizontal conic section. If I have it vertical, it's just going to change the cosine to sine, which is why we get that other form here. And we can convert that to Cartesian form. It's kind of a lot of algebra that I won't make you follow. But here are my notes for it. Whoops. So I did this out on paper, and I actually walked through with Calc 2 one year, the algebra. But basically, if we take this equation that I labeled 2, I can go ahead and square both sides and convert to Cartesian form. And I end up with this down here, which remember, E is a constant and D is a constant. So if E is less than 1, I can simplify it to basically an ellipse form, where I'm just setting H equal to all this huge mess. A squared equals this and B squared equals this. So it's definitely doable. It's just a bunch of algebra. I'm not gonna make you recreate this, but it's just to prove, hey, this is actually the equation of an ellipse in Cartesian form. But you can just take that as a given, and we don't need to do that this year. All right. So let's mess around with some of these polar equations. Find the polar equation for a parabola that has its focus at the origin and whose directrix is the line y equals -6. And since we have y equals as the equation of the directrix, we're going to be using this, the red circle, the ED over 1 plus or minus E sine theta. And so we already know that E equals 1. Because it's a parabola, right? And this says if it's a parabola, E equals 1. In this case, we'll take D equals 6. So in the case that it's y equals -6, we're going to be using basically part D of this figure. So this is when the directrix falls below the x-axis. You're going to, where y equals the opposite of D. So then D is the opposite of that directrix value. So D equals +6. And we're going to write it in the form R equals ED over 1 minus E sine theta. So for us, that's going to be R equals ED, which is just 6 over 1 minus E sine theta, so just 1 sine theta. And that should give us the correct version of that parabola that has a directrix at -6, but we can always just check that in our calculator. Our calculator has the ability to graph polar functions. So there are 4 options. If we go back, sorry, let me reshare this. So this diagram is going to be important. Oh, I'm sorry. So it's x equals d when the directrix is to the right. And it's then going to be in the form ed over 1 plus e cosine theta. It's x equals the opposite of d if the directrix is to the left, and then it's ed over 1 minus e cosine theta. And then likewise for vertical. So if it's above the x-axis, y equals the value of the directrix, and it's ed over 1 plus e sine theta, and
so just from knowing that the directrix is
1 minus. Correct. All right, again, so let's just go ahead and verify that this is giving us the conic we want in our calculator. Let me turn off my stat plot from last period. And turn on my polar mode. All right, so 6 over 1 minus sine theta. Let's see, my window, I should only need to go from 0 to 2 pi. There we go. So we got our focus at the origin. We got our directrix below at y equals -6. And we have a parabola. All right, so let's practice some more of this. Here we have a conic given by the polar equation 10 over 3 minus 2 cosine theta. Find the eccentricity, identify the conic, locate the directrix, and sketch the conic. All right. Well, what we want to do is get this into one of these 4 forms. So right now it's 10 over 3 minus 2 cosine theta. And we need it to look like one of these. So it needs to be ed over 1 plus or minus e cosine theta. So the first thing I need to do is get rid of this 2 coefficient on the cosine. Or I'm sorry, not get rid of that. That's fine. That coefficient is fine. I need to get rid of this 3, right? I want that to be a 1. So I'm going to divide top and bottom by 3, basically. So r equals then 10/3 over 1 minus 2/3 cosine theta. All right, so at this point, we should be able to identify what E is. Anybody tell me? Yep. Which is going to tell us what type of conic we have. If E is less than 1, it's an ellipse. So this is telling us that what we have here is an ellipse, right? All right. Now we know that the numerator, 10/3, has to be equal to E times D. That means D equals 10/3. Divide out the E, which is 10/3 over 2/3, which is 10/3 times 3/2, or 5. So D equals 5. And then the other thing we can identify is that since we have a minus in the denominator, that means the subtraction always means that the directrix is either to the left of the origin, or if it's a vertically opening conic, it's below the origin. So in this case, the directrix should be to the left. So I have my directrix at x equals -5, right? All right, so we can sketch it in the calculator, but how would we sketch this by hand? So the focus is at the origin. Our directrix is at x equals -5. And we're in polar form. So one thing we can do is figure out what the radius is when theta has certain values. So when theta is 0, for example, what's my radius? R equals 10/3 over 1 minus 2/3 cosine of 0. Well, cosine of 0 is 1. So what's 10/3 over 1 minus 2/3? That's 10/3 over 1/3, which is just 10, right? So when theta equals 0, the radius is 10. So this is the polar coordinate 10, 0. And then I could do it the other way. What about when the radius is pi? So I've rotated halfway around. So when theta equals pi, cosine of pi is -1. So I'm going to have 10/3 over 1 plus 2/3, which is 10/3 over 5/3, which is 10 over 5, which is 2. So when theta is pi, the radius is 2. So that's the coordinate 2, pi. And again, those are not Cartesian coordinates, those are polar coordinates, right? Oh, whoops, nope. Nope, should not be right there, I apologize. Because when we've rotated up pi, we're going to be on this side. So it should be here. That's the coordinate 2, pi. Right, so we've rotated to pi, and then our radius is still going in the positive direction, so it still goes in the direction of rotation. So these are basically our vertices. And our ellipse is going to look something like this. So let's just verify in the calculator. So now I have 10 divided by 3 minus 2 cosine theta. There we go. All right, we'll do a couple more examples. I think 2 more. So let's sketch another one. So r equals 12 over 2 plus 4 sine theta. First thing we're going to want to do is get this into standard conic form. So we need it to look like one of these 4 situations. And in fact, there's sine in the denominator, so it's a vertically opening conic. It's one of these 2. but we need that leading term in the denominator to be 1. So we're going to divide out whatever the leading term is right now. So in this case, that's 2. So I'm going to divide everything by 2. All right, so we get r equals 6 over 1 plus 2 sine theta. Great. So now we can definitively figure out what E is. My eccentricity is 2. So what's D? 3, right? Because the numerator is E times D. So D is 3. And the equation of the directrix. First of all, is it x equals or y equals in this case? How do you know? Because it's sine in the denominator. It has to be y equals. Is it going to be y equals D or y equals the opposite of D? Y equals D, and how do you know that one? Because it's positive in the denominator. Good. So it's y equals 3. The focus is always at the origin. What kind of a conic section do we have here? Good. E is greater than 1, which tells us what we have as a hyperbola. So last time when we were sketching it, we found the vertices of the ellipse by looking at when theta equals 0 and theta equals pi, since we knew it was a horizontal ellipse. This, you guys are telling me, is a vertical hyperbola, yeah? So what values of theta should we plug in this case to find the vertices? So we did the rotate, when it was a horizontal ellipse, we did the rotation 0 to pi, right? Because we know it had to be on the x-axis with the vertices of the major axis. This is a vertical hyperbola, right? Good, pi over 2 and 3 pi over 2. And that should give me the vertices in polar form of my hyperbola. All right, before I do that, I'm just going to graph my, there's my focus, here's my directrix. All right, let's look at when theta equals pi over 2. I'm going to have r equals, 6 over 1 plus 2 sine of pi over 2. Sine of pi over 2 is 1. So I get 6 over 3, which is 2. All right, and then at 3 pi over 2, r equals 6 over 1 plus 2 sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1. So I get 6 over 1 minus 2. So I get negative 6, right? So let's think about this. When we rotate to 3 pi over 2, which would be from here to here, right? So I'm facing down, basically. My radius is negative, so I'm going to count up in the opposite direction. So it's 1, 2, 3. And then it's 4, 5, 6. So there's my other vertex. So the lower one is going to be, the one below the directrix is going to be the vertex of the bottom branch of the hyperbola. And the one above the directrix will be the upper branch of the hyperbola. So something like that. I mean, I'm going to graph it better than this, but it's going to be like that and like that, right?
Sorry, what's that? Maybe the then is it still all?
Yeah. So these are coordinates. So this is the coordinate 2 comma pi over 2. And this is the coordinate -6 comma 3 pi over 2. So to find the asymptotes, we can just look at when the denominator equals 0. Which is to say when sine theta is -1/2, right? All right, well, the values of theta that will make sine -1/2, that's going to come from one of two triangles, either 30, 60, 90 or 45, 45, 90. The only one that will actually produce a ratio of 1/2 is a 30, 60, 90. So, and the ratios of the sides in a 30, 60, 90 are 1, 2, rad 3. So which one of those angles produces 1/2 as a sine ratio? 30 or 60? 30, because sine is opposite over hypotenuse, right? But we need it to be -1/2, not +1/2. Sine is going to be negative in these two quadrants, in quadrant 3 and 4, right? All right, so what angles does that correspond to? So I need a 30-degree reference angle, but I actually want to know the true angle, which would be the rotation from here to here. So what is that? Ooh, let's see. This is pi. What's 30? Pi over 6? 7 pi over 6. Good. All right, so one angle that will solve that for us is theta equals 7 pi over 6. That's one of our asymptotes. And the other one is going to be whatever the angle in this quadrant is. So the reference angle is 30 or pi over 6. But I want to know the true angle from here to here. So you can think of that as 2 pi, take away pi over 6. What is that? You got it. So remember that in polar form, theta equals a constant is the equation of a line, right? And so those two, theta equals 7 pi over 6 and 11 pi over 6, those are our asymptotes. So I'll just graph those. 7 pi over 6 is something down here. Oh, and you know what? I'm sorry. That's not actually how I should do it. The equations should be measured from the center of your conic. Meaning, I'm going to center my conic there. And then I'm going to graph as if that's the origin, theta equals 7 pi over 6 and 11 pi over 6. So they'll be like this. There we go. And then our branches should just follow the asymptotes. All right, and again, I'll just verify that in the calculator. Y equals, what do we have now? 12 over 2 plus 4 sine theta. The calculator actually, it has an issue with asymptotes. So it's kind of conveniently graphing them for us. It's not meaning to, though. It's thinking that the point up here and the point down here are on the same, they are technically on the same hyperbola, but they're meant to be connected when they're not. Calculators have issues when it comes to dealing with infinite end behaviors sometimes. All right. Last one. One nice thing about conics in polar form, although I would say that in polar form they're much easier to deal with because they're all conics basically have the same general form of the equation, which is just this r equals ed over 1 plus or minus sine or cosine theta. But it's much easier in polar form to rotate a conic than it is in Cartesian form. In Cartesian form, we can easily shift graphs, right? And that's just by add or subtracting to x or y. In polar form, it's much easier to rotate conics. So if we want to take the ellipse in example 2 and we want to rotate through an angle of pi over 4 about the origin, let's find the equation and then graph the ellipse. Well, let's talk about an ellipse. Let's say I have this ellipse in Cartesian form, x squared over, 4 plus y squared over 1 equals 1. If I wanted to shift that right 3, what would I do? How would it change the equation? If I just wanted to shift this ellipse to the right 3 units.
It'll just be like x minus 3 squared in brackets.
You would actually, you would subtract 3, right?
Yeah.
This shifts it to the right 3 units. And the way we can think of that is to get the same output here, all the x values have to be 3 units larger than they originally were, right? If all the x values are 3 units larger than they originally were, then everything gets shifted to the right 3. Does that make sense? All right. Same idea with a rotation. Except here we're looking at an equation of the form r equals 10 over 3 minus 2 cosine theta, right? That was our original ellipse in our first example. So if I want to rotate this through an angle of pi over 4 about the origin, all I'm going to do is subtract pi over 4 from my angle. So it's just theta minus pi over 4. And so to obtain the same cosine output as I would for my original equation, all values of theta have to increase by pi over 4. If all values of theta increase by pi over 4, it's going to rotate all the points through the angle pi over 4. So let's just check what that would look like. So I'll graph the original one and then I'll graph the rotated one. So the original was 10 over 3 minus 2 cosine theta. There's that ellipse. And I still want to keep the focus at the origin. I just want to rotate it through pi over 4. So now 10 over 3 minus 2 cosine theta minus pi over 4. There we go. Did you say you don't like that?
I like that. I find that satisfying. I don't know why.
So we can shift it all the way around, right, if we subtracted pi. Let's try that. So 10 divided by, oh no, I haven't
Wait.
been sharing
I
it.
can't see what's going on.
I'm sorry. Here you go. 10 divided by 3 minus 2 cosine. Let's do, I don't know, how far do you want to, let's go even crazier. Let's 3 pi over 2. I'm glad administration is not observing me right now. They would be like, inappropriate, Tolar. Kids are not prepared for that. So it distorted it because the screen isn't square, it's rectangular. But if I do zoom square, I think it'll fix that. There you go.
That's the original one.
Yeah, it kind of is, right?
Cool. Huh. I like that.
Cool. That's it. I think we have a problem. Well, hold on. Let me make sure that's it. Oh, here's a cool diagram just to show you how the eccentricity impacts the shape. So the closer to 0, the more circular. The closer to 1, the more elliptical. When it is 1, we get a parabola, and then when it's greater than 1, we get hyperbolas that become increasingly wide as the eccentricity grows. All right, 10.6 part 1 problem set. There you go. You got about a half hour to get going on that. Zoomers, you can log off and work on it if you like. I have office hours today at 11, so I'll just be in here if you have questions. If you want to stick around and work on it with me sitting here staring at you or staring at the blank screen, that's fine. Oh. Yeah. Let me pull up my key. You got one wrong? Oh. 5. Oh, I think you had the wrong bounds. I think it should be -2 to 1 here. Oh, okay. Did I put a hint on there that it intersects itself at negative 2, 3?
That's what I was thinking just now, but what we did with that is we talked about
Right. Yeah. All right. Let me check. All right. So the curve intersects itself at negative 2, 3. So t cubed minus 3t equals negative 2. Yeah, this one's actually t squared plus t plus 1 equals 3. T squared plus t minus 2 equals 0.
Oh, I
T
know.
plus 2 times t minus 1, right? T equals negative 2 times 1. I don't know.
Oh, we were thinking DFC.
You're finding the slope.
But that's
I don't know why. You just want to find where it intersects itself.
So, okay, what we were doing is we were finding vertical asymptotes because on the graph,
You're finding where it has a vertical slope, not necessarily a
Right,
vertical asymptote.
because that's not that was the part of the I think the
Yeah.
thing is that, so, just because it has an intersection at that point, does that mean that it only goes that far? Because when you graph it, it's like,
That would make sense if you were integrating with respect to x, right? But you're integrating it in parametric form, so you're integrating with respect to time. So you want the times where it it does this, right? Like,
yeah.
so you want the time from here
Sure, okay, that
to
makes
here.
okay. That's how you
Yep.